All right, welcome to our last class of electromagnetism, day 10. So let's get started with the homework. So we have this LC circuit, and we're given some information about time t equals 0, and you'll find the maximum charge on the capacitor. So we know that the total energy equals Q squared over 2C plus 1 half Li squared. And then we can plug in this. We know charge is 0, current is 2. So then we get this is 1 half L. You can substitute L from the given and this current squared. And then the maximum charge. So this will also equal 1 half times the maximum charge, Q max, right? And you can plug in C and then you can solve for Q. All right. And then for part B, it's asking at what earliest time is the rate of the energy stored the greatest. So we can take the derivative of the, oh, sorry. We should take the derivative of the q squared over 2c. So d dt of q squared over 2c equals what? So we should remember that q equals q max times sine omega t. So we can plug this in. Um, we can plug this in over here, take the derivative, and eventually you'll get that the earliest time. So eventually you'll get that the earliest time happens at um you'll get some expression in terms of 1 over root LC and pi and times some factor of pi. And then you can solve this. And then you can plug this t back into here to get q, and then back into q squared over 2c to get the maximum rate. So are there any questions about that? If not, we can move on. So we have a coil with a certain inductance, we have an unknown resistance, a capacitor, and an alternating EMF of frequency, and we have the phase difference. So we know that if you remember this result, you can also look back at last class, we derived this. We have XL minus XC over R. The tangent of the phase difference equals XL minus XC over R. So now I can literally just plug in the numbers. Um, and yeah, remember that XL equals omega L and XC equals 1 over omega C. And yeah, you're given frequency, so you can get omega from that because omega equals 2 pi f. So yeah, plug all these things in and you can solve for R. Any questions on that? If not, on to the next question. So we want to solve for the complex impedance Z of this. So we have, remember that, so we have our resistance R. Remember that the complex impedance of an inductor is omega L. For a capacitor is 1 over omega C. And since all these elements are in series, we have that the complex impedance is simply the sum of these. Oh, sorry, this is complex impedance, so there's an I. And then we just add all these up, and you get your complex impedance, right? And then they're asking for the current as a function of time. So we have this EMF over here. So I of t equals V of t over the real part of the complex impedance. Because remember, this impedance that we found here, this is a complex impedance. So we have to take the real part. And yeah, you can do this to get your I of t. You can plug in this for V of t and you can solve. Are there any questions about that? If not, we can move on to the for the problems today. Today's an extra problems day, so yeah, we're just gonna be going over a lot of problems. All
Yeah.
right.
Uh, yeah, let's go on to the first problem. It's going to be about induction. So there are two long solenoids that are encircled by loops with two resistors R1 and R2 as shown in the figure below. The right solenoid produces a magnetic flux. Flux equals alpha times time out of the page through itself where t is the time elapsed, right? From a reference point. While the left solenoid produces a magnetic flux, flux equals beta t out of the page through itself. The voltmeters are ideal and possess infinite resistance. If each voltmeter measures the voltage across its ends via a path through itself, determine the readings of the voltmeters. Okay. How about let's spend maybe 5 to 10 minutes on this problem, and then after that we can go over it. Yeah. All right, let's go over this problem. Okay. So let's take a look here. So we have the right solenoid. It produces this flux over here. It's coming out of the page, and the left solenoid is also producing a flux that's coming out of the page, right? And notice that the flux, we're saying it's alpha times like the time, right? Meaning that the flux is increasing out of the page. And if the flux is increasing, let's for example, we look at this solenoid over here, the right solenoid, the flux is increasing out of the page. That means there's going to be an EMF induced that will try to oppose the change in flux, right? So we have a flux that's coming out of the page. So the current, if we want to use the right-hand rule, the EMF would have to be curling in this direction. This way, oh, oh wait, yeah, the EMF will have to be going curling in that direction. Because that way, if you use your right-hand rule, you'll find that the flux generated by this induced current will be pointing into the page, while the flux produced by the solenoid is increasing out of the page, right? Okay, so how do we find the exact amount of flux? We know, let's say epsilon r, right? Epsilon r, that equals to, wait, what does that equal to? That equals to, wait, so we have this one, right? Equal to alpha, right? Okay, if we have that equals to alpha, right? Then what will be the current in this loop? Well, if I know that uh, the total amount of voltage drop in that loop is alpha, then I know that the current, right? So the current I would be equal to alpha over R1 plus R2, right? So that's just voltage divided by resistance of divided by R1 plus R2, because this is the only loop of current that we have in the circuit, right? Because we're assuming that because these voltmeters have infinite resistance, there's no current going through them. So everywhere, oh, yeah, everywhere in the, like in this, let me use a different color. Everywhere in this loop over here, we have the same amount of current. So I'll just let that be I, and that's our current I. Okay. Now, how do we find, yeah, so we want to find uh the voltage readings on each of the voltmeters, right? Well, the reading on the right voltmeter is pretty easy. Why? Why is it easy? Well, it's because there's no flux going through this loop over here, then I know that for example, if I let this be V2 and this be V1, then I can just say that V2 equals to the current and then times R2, right? So we're just getting V2 would be equal to alpha R2 and then divided by R1 plus R2, right? So that's pretty simple for the right voltmeter. That's what we're getting. Now, how do we find the voltage on the left voltmeter? So V1, right? That's a bit more complicated. Why? It's because we have another solenoid here and it's producing its own EMF. So how do we take that into account? Well, we know the left solenoid, right? The flux is beta T. So we're given, let me draw on the left side. So flux phi B, basically the left solenoid, right? It's producing a flux that's equal to beta T and it's coming out of the page, right? So meaning that the EMF on the left side would be equal to beta, right? And what direction is that pointing? Well, because the flux on the left solenoid, it's increasing out of the page, then I know my EMF will have to be curling in this direction over here. So like this, right? Because it will oppose the change in flux due to the solenoid. And then how do I write like a voltage equation? Well, okay, so I know the current through this resistor over here, the R1, that's still equal to what we found for I, right? So I'll say there's a voltage drop through R1, so I times R1, and there's also a voltage drop due to the EMF. So let's say plus uh epsilon L, and that will have to be equal to the voltage rise that we see on the voltmeter, right? So IR1 plus epsilon L equals to V, oops, equals to V1, right? And then, so yeah, we can just solve for V1 now, right? So we know what I is, know what epsilon L is, so we just get, okay, I R1 is gonna be alpha R1 over R1 plus R2 and then plus beta, right? Plus beta, that'll equal to our V1. And that is our final answer for V1. So we got V1, we also got V2 over here. And yeah, yeah, we got the readings on each of the voltmeters, and yeah, that completes the problem. Uh, any questions on this? So basically the overall idea is just remember uh your Faraday's law, right? So remember epsilon equals to negative like d flux over dt, right? And then just remember it opposes the change in flux. And also when you're writing your sort of like your Kirchhoff's loop rule, right? You got to take into account the EMF that's induced, right? So for example, on the loop on the right, there's no EMF induced in that loop, right? There's no solenoid going through that loop. So we can just simply say V2 equals to the current times the resistance, right? But now in the left loop, we have the resistor that causes like a change in voltage. We also have the changing flux of the left solenoid that induces an EMF, right? And then we have to get that into account to get the final reading on the left voltmeter. And yeah, if you get the conceptual idea, it's not too hard. But otherwise, yeah, it's a good review of the induction and like the induced EMF. Yeah. Let's go on to the next problem. Okay. Yeah. A square loop is exiting a constant and uniform magnetic field B with a constant velocity V perpendicular to the magnetic field. Find the EMF induced in the loop when the left end of the loop is at a distance x from the right boundary of the magnetic field. Find the force required to maintain the velocity of the loop. The loop has resistance R and negligible self-inductance. Okay. So yeah. Remember last problem we were talking about induced EMF, right? So basically, when we're talking about epsilon is negative d flux over dt, this is a similar idea, but you also have to combine it with the idea of Lorentz force. So how about maybe 5 minutes to do this problem, and then we can go over it. Yeah. All right, let's take a look at this problem. All right. So remember we have a square loop over here. Oh, me, give me a second. All right, yeah. You have a square loop over here, and then we're pulling it to the right at a constant velocity, right? So first off, okay, we have a magnetic field over here, and the square loop is exiting the magnetic field. So what does that mean? Well, because the square loop is moving out of the magnetic field, there's going to be a changing magnetic flux through the square loop. If we have a changing magnetic flux, of course, we have an induced EMF, right? So then one might ask, okay, why is there a force required to maintain the velocity of the loop? Well, that's because if we have an induced EMF, right? So there's going to be current flowing through the loop. And then you know that if you have current flowing through a loop and you also have a magnetic field, then what does that mean? That means we have a Lorentz force, and there's going to be a force that will be opposing the motion of the square loop, right? You think about it. If a you have the square loop and it's moving out of the magnetic field, by Lenz's law, there's going to be a force that will try to oppose the change in flux, right? There's going to be a force that tries to pull it back into the magnetic field because it wants to oppose the change in flux. So now let's look at it quantitatively, right? So that was the physical picture. Make sure, like, before you do a problem, you get the physical picture right, okay? So first, I want to find what's my induced EMF, right? They ask us for it. What's the EMF induced in the loop? Uh, okay, so remember we have epsilon. Let me zoom in for a second. Yeah, we have epsilon. Remember that equals to negative d flux over dt, right? D flux over dt. Now, what is our flux? We need to find our flux to find the epsilon, right? So first off, the only part of the loop that has a flux going through it is that part. So it's specifically going to be this triangle over here. So that's pretty simple. We're given that this length over here is x, right? So of course, this is also x because it's square. So we get flux is equal to, so we'll be doing d flux, right? The flux will be equal to, first off, the area of that region, so x squared, and then times b, right? Because we're finding the magnetic field times the area, the d of that over dt. Now, okay, how do we find that? Well, we also know that dx over dx dt, that's equal to v, right? And v is always constant because, like, this is basically sort of like a distance. If you're doing dx over dt, you're essentially just finding the velocity of the square loop. So if we use the chain rule here, then we'll just be getting 2x v and then times b, correct? So we just found our epsilon. And then just to make sure, what direction is our epsilon curling in? So will be the direction of our current, right? Uh, well, okay, so we have the uniform magnetic field. It's pointing, which way is pointing? It's pointing out of the page, right? Yeah, we're given its dots, so it's pointing out of the page. What does that mean? If the flux if the flux is out of the page and it's decreasing, that means that there needs to be an EMF induced that'll create a magnetic flux out of the page, right? Like just to repeat that, right? I have a magnetic flux. It's pointing out of the page, but it's decreasing. I want to counteract that decreasing flux, right? So I want to create an EMF that'll create a magnetic field that'll point out of the page. And what direction will that be in? Well, it will be pointing in this direction, right? Oops, this direction. This will basically be the direction of my current, right? Because if you use your right hand rule, this way you have a magnetic field that points out of the page, and that counteracts the decreasing magnetic flux that was pointing out of the page, right? This is the direction of our EMF, or like our current, right? So I know that my current, let me switch back to green. So my current I would equal to what? Well, it would equal to 2x v times b then divide by R, right? Okay, so I found the current in my loop, and then no, 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 no. Give me a second. All right, yeah, it's good. All right, so all right, I found my current now. Okay, we're told that there's going to be a force required to maintain the velocity of the loop. And what nature of that force is, well, it's going to be due to a sort of Lorentz force, right? So let's look at it. Let me clear, let me erase the drawings here so that we can have a better picture. All right. So my oh, but this will be the direction of my EMF. What? Oh wait, this is direction of my EMF. Okay. So it curls in that direction. Okay, so that's just the direction of my currents, right? Now, if I want to find the Lorentz force, how do I find that? Well, first, the velocity of the square, or so first, like Lorentz force, right? That's due to the motion of each charge. So each charge, it has two components of velocity, right? First, it has a component of velocity due to the velocity of the square loop itself. So, if I think of the square loop as a whole, it's moving to the right with a velocity of v, right? But also, because there's a current in the loop, each charge also has a velocity pointing in the direction of wire loop. So, for example, if I look at a charge maybe over here, I'll represent it with that red dot, then it'll have two components of velocity, right? It'll have a component that way, which is due to the velocity of the square loop. It'll also have a component in this direction along the wire. Oh, maybe I'll redraw that. So it has another component of velocity in that direction. Why is that? It's because there's a current in the square loop because there's an EMF induced, right? So let's look at the Lorentz force due to both of these, okay? So let's look at, okay, Lorentz force due to this component of velocity, right? Remember, we have Lorentz force, so uh, can write the Lorentz force as, let's say, FB or yeah, F would equal to the magnetic part of the Lorentz force is just Q and times V crosses the B, right? And both V and B are vectors. Now, okay, so the square loop as a whole, every charge on it has a component of velocity that's pointing to the right with a velocity of V, right? So that means the square loop as a whole, if I use my right hand rule and do my V cross B, my V is pointing towards the right, my B is pointing out of the page, meaning that the square loop, the entire square loop, it has a velocity, it experiences a Lorentz force that's pointing downwards, right? So this is going to be, let me, oh, so as a whole, if I draw maybe like a force diagram over here, this is my entire loop. So loop, it has an it has a Lorentz force. It experiences a Lorentz force as a whole that's pointing downwards, right? It's gonna be yeah. So if you do V and then crosses your B, right? Your B is coming out of the page. So you'll get a Lorentz force downwards, F. Uh let's call it FV because it's due to the velocity of the loop. That equals to okay, how do I find the total Lorentz force? Well, it'll just be, let's say, Q total, and then B cross B, right? And because V and B are perpendicular, I can just write it's equal to Q total and then times V and then times B, right? Okay, so let's now look at the other component of velocity of the charges, right? Which is actually along the direction of the wire. Okay. So if I still look at like my charge over here, has a velocity, oh, so Q total, actually Q total, it will have to be like, all right, let me clarify on the Q total. So Q total, I'd say, uh, let's say equal to Q that is in the B field. So Q, so when I say QB, it'll just be the total amount of charge that is in this region, right? Because it has to be within the magnetic field to have like the Lorentz force, right? So sorry about that. Right. So uh maybe let's look instead at charge over here. So say over here, this is my charge, and let's look at the forces and the velocity and forces, right? So first it has a velocity, this direction along the wire. It also has a velocity in this direction due to the motion of the entire loop, right? So what does this mean? Well, let me say I'll draw a free body diagram for that charge, okay? So like some dq, right? Or I'll just say q, let's just say q. So some q. Okay, over here. So first it has the Lorentz force that we said is due to the velocity of the entire loop. So that points downwards. Let's say it's FV, and that equals to QVB, right? Let's ignore it for now because the problem implies that we want to look at the velocity that like basically the force that counteracts this velocity. So basically in the opposite direction of the current velocity. But we can still talk about this if you want. But the main thing that we're concerned with is the Lorentz force due to the other component of the velocity, which is in the direction of the loop. So in the direction of the loop, right? My velocity is pointing like in the direction of the loop. If I do the Lorentz force, then you'll find that the Lorentz force will be pointing in this direction, right? This will be F, let's call it F due to current. So I'll say Fi. And then for this charge we're looking at right now, will be pointing at 45 degrees angle, right? So this will be my Fi. And what's Fi equal to? Well, we're actually concerned with the total Fi if we integrate along uh the region of the wire that's in the magnetic field, right? So you'll notice that if I look at a charge over here, it'll experience, the usual uh will experience the FB, which is just force due to the velocity of the current loop as a whole. And then the Fi it experiences, so velocity due to like the fact that it has a current, be pointing in this direction. So notice if I integrate from like in the entire region of the entire part of the wire that's in the region of the magnetic field, it's only the horizontal component that matters because the vertical component, if I decompose each of these forces, right, has a vertical component, also has a horizontal component, looks something like that. The vertical components, they all cancel. I'm only concerned with the horizontal component, right? So in total, what I'll be doing is I'd be doing my Fi. Okay, so what's my Fi? Fi would equal to say dq, and then or you also have Lorentz forces equal to like I and then dl and then times the magnetic field, right? So I'd say Fi is equal to I uh dl, right, cross B, right? Now, when I do the cross product, right, cross product still remains, it still remains as we can treat it as a scalar product because the velocity and the magnetic field are perpendicular, right? But because we're only considered with the vertical component, we multiply it by the sine of this angle, right? But that angle is just 45 degrees. So we'll say sine 45 degrees. We're just doing the integral of this, but basically the integral is we're just like, because we're integrating across DL, right? And I, B, and sine 45 degrees, they're just constant everywhere. So it's also equal to I, and then what's the total length? Oh, wait, so first, let's do I, B, sine 45 degrees, sine 45 degrees, right? And then what's the total length we're doing? So like what's the integral of dl? Well, we're basically integrating. We try to draw this nicely. So basically integrating across this over here. So the total integral of dl is just that, like that sort of triangle I drew. So then what's that equal to? Well, we know the integral of dl, that will be x 2x divided by sine 45 degrees, right? And so in the end, sine 45 degrees, it cancels, right? And then we can also plug in what we got for I, right? Plug in over there. So what are we getting? Well, we'll just be getting, so 4 x squared, 4x squared v, and then because we're multiplying by b again, right? So vb squared and then divide by r. 4x squared. Yep, that looks correct. This will be our final answer because the net force, if I look at the loop as a whole, it's going to have a net force pointing towards, like, there's going to be another force pointing towards the left, which will be like Fi total, right? Is that's due to, that's like the Lorentz force due to the motion of the charges in the direction of the wire loop. So basically, it's the Lorentz force due to the current and not the Lorentz force due to the overall velocity of the loop. Does that make sense? Okay. Yeah. So uh this is basically the final answer. If you want, you can also include like you also have to have the force due to the velocity of the entire loop. So basically QVB. Uh but basically the total force you need in the direction opposite of the velocity would be this. So 4x squared b squared divided by big R. So divide by resistance, right? Yeah. Does that make sense, everyone? All right. If so, let's go on to the next question. So basically for this question, remember that overall, it's just that if you have like the square loop, it's exiting the magnetic field, there's going to be an EMF induced because the flux is changing, right? And then due to the EMF, there's going to be a current induced in the wire loop. And because there's a current, there's going to be a Lorentz force because like part of the wire loop is still in the magnetic field. So there's going to be a Lorentz force, and once you decompose the velocity and the forces, you'll find that there's going to be an overall net force towards the left, so opposing the motion of the loop. And there's also going to be an overall net force pointing downwards. But what we're really concerned with is the net force pointing towards the left. So, yeah. All right, let's move on then. Let's go on to the next problem. All right, yeah. So this is just a DC circuit. Remember your Kirchhoff's laws and uh yeah, take like a few minutes for this one.
All right. I think we can go over this now. So you can see what I drew. So we'll assume that we have our current I1 in this loop going clockwise and I2 in this loop going clockwise. So remember our Kirchhoff's loop rule. Um, so we have minus 14 for this, minus 6 times the current in this branch is going to be I1 minus I2, right? So we have I1 minus I2 plus 10 for the 10 volts, and then minus 4I1 is 0. And then the second equation is from the bottom loop. The bottom loop, we have that um, minus 10. So minus 10 here, minus 6 times I2 minus I1 minus 2I2 equals 0. So this is equation 1, this is equation 2. So equation 1 just becomes 10I1 minus 6I2 equals sorry, minus 10I1 plus 6I2 equals 4. And equation 2, if you simplify, you get 10 equals 6I1 minus 8I2. And you can solve this. It's a system of equations. And yeah, you're gonna get I1 equals something and I2 equals something. And they're asking for the current through the 2 ohm resistor, so your answer is gonna be whatever I2 is. Any questions on that? All right. If not, we can move on. All right, so this is a very interesting DC circuit problem. You have a cube, it's composed of wires, and each edge has a resistor of 1 ohm resistance. And we want to find the equivalent resistance between two opposite vertices of the cube. So we'll say we want to find the equivalent resistance between A and D. All right. So I'll give you a couple of minutes to work on this. This is a very classic problem, and yeah. All right. Hopefully you've had time to think about this. If you haven't figured out, that's fine. I think we'll just go over this now. So this is a problem centered around symmetry. So we notice that B, H, and F, I'll use a different color. They're like they're symmetrical, right? Because they're all one edge in a sense away from A and two edges in a sense from D. So they're symmetric. So by symmetry, they'll have the same potential. They'll all have the same potential. You can call it like V1. And similar reasoning, C, E, and G will all have the same potential. We can call that V2. That's the first observation, is that we have these. So this, so sorry, let me back up. So these th two groups will make three separate like groups of resistors. So we'll have these three resistors. We'll have these six resistors, and lastly we'll have these three resistors. We'll have the we'll have the same like grouping. And the thing about these groups I just highlighted in blue, pink, and green is that they'll be in parallel because since they all have the same potential, right? The potential across this resistor, if A is 0, let's say, it will be V1. And same thing with this resistor, same thing with this resistor. So they'll all be in parallel. Same reasoning with with the three green resistors and with the six pink resistors. So combining all of this information, we can actually simplify this 3D cube into a 2D diagram. So in this 2D diagram, this is supposed to be D, by the way, we have these three resistors, our first group, the six resistors in our second group, and the other three resistors in our third group. And since each is 1, 1, 1, you can do that the equivalent resistance is 1 over 1 over 1 plus 1 over 1 plus 1 over 1 is 1 over 3 is 1/3. Same thing here, you can get 1/6. Same thing here, you can get 1/3. So the equivalent resistance, since these three groups are in series, will just be 1/3 plus 1/6. Oh, this is ohms. Should write that. Always write your units. Plus 1/3 ohms. And if you add these, uh, you will get 5/6 ohms is your equivalent resistance. And if you were given like the voltage between A and D, if you're giving VAD, then you could like find the current and so on. So are there any questions about that? This whole problem? There are a lot of variations on this. You can search it up. There are some USAFA problems with variations on this. There's a lot of problems out there with variations on this. So if you're interested in this, you can search it up. Yeah. All right. If there are no questions, we'll go to the next problem. Yeah, this is about RLC circuits, so yeah, I'll give you a couple of minutes or more to work on this.
Let's take a look at this problem. So, okay, we're looking at an RLC circuit here right now, and then you might be thinking like, oh no, we have to solve like a complicated differential equation or something, right? But actually, y like you could solve a complicated differential equation and you'll get like, for example, you'll get the charge on the capacitor as a function of time. I notice that the question it's only asking us for what's the charge stored by the capacitor if the switch is closed for a very long time. So switch is closed for a long time. That's a really big key word because we're assuming that like if we leave the circuit there for a very long time, then we're gonna get what's called like a steady state. So we're gonna assume the steady state is where there's like there's absolutely no current everywhere. And then on the capacitors, the charge on the capacitors is like constant. Okay. So right now we're looking at where the switch is closed first, right? So we'll close the switch in the beginning. And then so how do we get like, we have zero current everywhere? Well, okay, notice we basically have we have our sort of battery there, and then we got like one parallel connection that has a capacitor and a resistor, and another one that has an inductor, and another one, we have capacitor here and resistor here, okay? So what does it mean when we have a steady state, right? So when we have a steady state, okay, we have zero current, as I said. So how will that translate quantitatively? Well, so if there's zero current, the voltage difference from here to here must be zero. Because if we had a voltage over here, so let me erase some stuff. So if for example, we had let's ignore the capacitor for now. If I had a battery over here, then there's going to be a current, right? But the purpose of the capacitor is that if I have the capacitor here, and then let's say it has its let's say this is where the negative charges are stored, and this is where the positive charges are stored, right? So what does this mean? There's going to be a voltage drop over here. There's going to be a voltage rise over here. And in total, I want this voltage drop and voltage rise to add up to zero. And this way, there's going to be no current everywhere because there won't be an EMF, right? There won't be a battery. So what does that mean? Well, we need to have Q1 over C1 to equal to epsilon, right? So we're just getting Q1 is equal to epsilon times C1, right? Now, how do we find the charge on capacitor 2? Well, because there's no current, right? There won't be a voltage drop across this resistor, right? And I know that the voltage drop over here, delta V is equal to zero, right? And because this branch over here is connected in parallel, I know that this also must have a delta V of zero, right? And the only way this will happen is if we have, wait, so we're given there's zero current. So there's no voltage drop over here. So this has delta V of zero, right? Delta V equals zero, meaning that the only way for this to happen is that there's no voltage drop across the second capacitor. That means Q2, Q2 over C2 is equal to zero, right? What does that mean? Well, that means we must have Q2 equals to zero, right? So this is in the case where we have switch is closed, and then we're leaving the switch closed for a very long time. Pretty simple, right? Uh, by the way, we don't need it. Wait, you can see there's an inductor here, right? And you might think, okay, does that change anything? Okay, the switch is closed. Remember, we have the voltage drop across an inductor. We have delta, let's say V inductor, VL, that will equal to your L, your inductance, and then times your di over dt, right? I dot. And then because we are assuming it's a steady state, we'll say that I dot is equal to zero. I dot is equal to zero, so that means that VL is just equal to zero. So we can treat this branch over here as just like a single wire. Okay. And that's really convenient because what does that mean? If it's just a single wire over there, okay, first off, If there was current, all the current would be flowing along that wire and there will be no current over here. If like if let me clarify that. So if we had yeah, this is basically like a short circuit. So it's a wire with zero resistance, right? So if this branch over here had resistance, there would be like no current flowing through there, okay? So basically we the inductor there, because it's a steady state, there's no voltage drop across it. Does that make sense? Right. So now we're asked if the switch is open from the start in the beginning. So that's a bit different. Let me erase everything. All right. So we're given that the switch was open in the beginning. That means we can just ignore this branch over here because it's basically like an open circuit. So let me redraw the circuit, right? Remember, we can always reorder, like if everything's connected in series, which is in this case, right? We can just reorder all the circuit elements. So let me redraw it. So we have in the case where the switch is open, then we have can say there's going to be like one resistor. Let's say we just replace it with one resistor with equivalent resistance, which is R1 plus R2. And then we have two capacitors, right? Later we can replace it with one capacitor, but let's just say we stay with two capacitors like this. And then this has C1, this has C2, right? And this is epsilon. Okay, so right. Okay, so how do we get that it's so after a very if the switch is open from a sorry, yeah, if it's at a very long time, what will it look like? Well, okay, so I must have okay, epsilon must equal to uh Q let's say Q. By the way, uh, we know the charges on these two capacitors are equal because they're connected in series. They have the same initial amount of charge, right? So they have the same amount of charge. So I'll let that amount of charge be Q, right? So Q over C1, or I'll pull out the Q, right? So Q times 1 over C1 plus 1 over C2, and then plus like some voltage across the resistor, right? That equals to epsilon. Well, okay, I know that because the switch was closed for a very long or switch was open for a very long time, then the current in the circuit is equal to zero, right? Because why is that? Because if the charges on the capacitors is constant, that means my Q dot is equal to zero. But I also know that my current in the battery, like current through the circuit, right? My I is equal to the Q dot. But if Q dot is zero, that means the current in the circuit is zero. So that means there's no voltage drop across the resistor because, voltage drop across the resistor is obviously the current times the resistance, right? And I know the current zero. So that means I just get this over here. So what's my Q? Well, then I'll get, in this case, let me draw in green. So I'll get Q, say open would equal to epsilon and then 1 over C1 plus 1 over C2. And then, by the way, this is the charge on both of the capacitors. So this also equals to Q1 equals to Q2. Yeah, that's our final answer for this part. Yeah. Any questions on that? All right. If not, yeah, basically the overall idea, uh, you don't have to solve any differential equation. Just remember if keywords is like if you see that the switch is closed or open for a very long time, then you can assume that at like when time equals to infinity, you can see if there will be zero current in the circuit. For example, in when the switch was open, right? We said that the charge on the capacitors is all constant. So we can say that the current in the circuit is equal to zero. And that really simplifies the problem because, for example, you can like in the first case, we just treat the inductor as just like a simple wire, right? We don't need to take into account that like the voltage across the inductor is like L times I dot, right? Because you know your I dot is zero, so it's just like a short circuit, right? And in this case, so we just said that the charge on the capacitor is constant, so there's no voltage drop across the resistor. Yeah. Just keep those in mind and you should be good. All right, we're almost running out of time. So yeah, we're basically out of time right now. So we'll skip the last problem. I'll probably send you guys a solution of the last problem, just about an AC circuit. Yeah, this is just an AC circuit. It's really similar to a problem we did last week. Just remember to solve this problem, use the complex impedance so you know that the Z total complex impedance, we'll say it's equal to, this one is I 1 over I omega C, right? So 1 over I omega C, and then what's the complex impedance of this? Well, remember complex impedances, they're just like resistances, they add in series and parallel. So like if you have two elements and they have two complex impedances, right? And if they're in series, you'll just do like Z1 plus Z2. And if they're in parallel, you'll do 1 over Z1 and then plus 1 over Z2, right? So similarly over here, then it'll just be plus 1 over, and then the complex impedance of the inductor is I omega L. So right, so 1 over I omega L, and then plus 1 over R, right? Because the complex impedance of a resistor is just R. This is our total complex impedance. Uh, all right, and then we want to determine the current through the resistor. Okay, well, to find that, just remember, overall, like we're given that, let's say that's equal to the voltage, right? Then we'll just say that, okay, so the current through the capacitor, we know it's equal to I capacitor would equal to V over Z, the total Z, say Z total, where V is just given to be this over here, right? And then, so this is V over Z total. And then to find IR, or current through the resistor, remember, it's just like resistors, we'll do IR equals to IC. And then remember, the current splits like at that junction. And remember, it's inversely proportional. Like for each branch, the current through it is inversely proportional to its complex impedance, right? So it will be equal to IC and then times the complex impedance of the inductor divided by complex impedance of the inductor plus complex impedance of the resistor, right? So we'll just get it equals to your, okay, so V divided by Z total, and then times ZL plus ZR, and then times ZL on the top. And then, yeah, that's our, basically you just plug in what you know for ZL, Z total, ZR, right? And then NNV, right? And then this is going to be equal to your current through the resistor, right? So current through a resistor as a function of time. And then if you want to find when it's at a maximum, you can just say that it will be at a maximum when dIR over dt equals to 0. And then you'd expect the current to be at its maximum. And for power, all right, for this particular C, determine the power dissipated through a resistor. Well, that's simple. Remember, P resistor is just equal to like your current I squared, so IR squared, and then times the resistance. So yeah, I'll probably release like a full solution for that if you guys want, but this is an overall idea of how you do it. Just remember the idea of complex impedance is really, really useful I highly recommend like brushing up on complex impedance. It's gonna basically simplifies AC circuits a lot. Yeah. Uh, Last thing, let's go to the next slide. All right, so thank you everyone for coming to our Paragon X EM course. I hope you guys learned a lot. It's been really fun teaching you guys. Sean, do you have any words to add?
No, yeah. It was, yeah, pretty fun teaching you guys. We did a lot of problems. Yeah.
Yeah, so
And
yeah, keep going.
oh yeah, sure. And make sure to fill out this feedback form. I think we'll send it out in the email along with the solution to the last problem and maybe some homework problems. But yeah, make sure to fill out this feedback form. It'll really help us and instructors who teach electromagnetism next year. It'll really help them. So yeah.
Yeah, and then stuff to do after this course, definitely like review the lecture recordings, lecture slides, and then it'll be really good for you guys to like do the homework on your own, and then like if you guys want to like do the homework again and like email it to us, like we're totally like happy to read over your homework submissions again, and then like we can give you feedback. And if you have any questions on EM or like physics in general, you can always email us or like ask questions in the Discord. I know in Discord there's like a special channel for like your questions. So like just drop your questions there. Also after this course, other than like reviewing course material, definitely recommend some like textbooks. So in my first email, or I'll add them to the email I'll send after class, but there are some pretty good textbooks you guys should read if you want to learn more about EM. But other than that, yeah, it's been great teaching you guys. Hope you guys learned a lot, and yeah, thank you so much for coming. All right, bye bye.